For 11.2 and 11.3, I have put them together because they both sort of go with one another. So again, talking about populations and how they can change and evolve. So natural selection acts on the distribution of traits. If we're talking about a single gene trait, you'll end up seeing uh, one of the traits becoming more dominant in a population. And it doesn't matter whether it's the dominant trait or not, it's going to be what's best suited for that environment is going to be what you would start to see happen more and more of. When we're talking about a polygenic trait or a normal distribution graph that like is a bell curve, you're going to end up seeing the middle of that curve is the average, and we'll end up seeing the graph shift left or right or up or down. That's going to be what we end up seeing with natural selection. So the highest frequency near the mean is near the mean value. Frequencies decrease towards the extreme value. Traits not undergoing natural selection have a normal distribution. So natural selection can change the direction of a trait in one of three ways. So you have microevolution as evolution within a population, or if you want to think about it as looking at evolution on a genetic scale. So seeing what traits show up more often. So that is what that would be. So observable changes within the allele frequency, and it can result from natural selection. Natural selection can take one of three paths. Directional selection favors the phenotypes at one extreme or the other. So in the picture that you see there, you can see that the graph is shifted to the right. So the high drug resistance bacteria ended up being the best suited for that environment. So it ended up shifting to where that is now the average for that population, and that's going to be the ones that are the best suited for that environment. Another is stabilizing selection. So stabilizing selection favors the intermediate groups. So what you end up seeing here is that the middle of the graph is the best suited. So the average is the best suited, and you're going to see the graph, that bell curve, is going to narrow down, and it's going to end up making that population is going to really only have like the middle of the row individuals. The final is disruptive selection, and it favors both extreme phenotypes. What you would end up having happen here is the middle is not good and the ends are the most fit. So you're going to end up eventually having the graph split into two distribution curves. And you would end up seeing that here's what the best of these populations would be. And again, this would be one way that evolutionists would say, here's how a population could split. So looking in section 3, natural selection is not the only mechanism through which populations evolve. So gene flow is the movement of alleles between populations. So gene flow occurs when individuals join new populations and reproduce. So that means like it's going to be immigration or emigration. So an organism is going to be coming into a population or leaving, and they bring new genes in. So the gene flow keeps neighboring populations similar. Low gene flow increases the chance that the two populations will evolve into different species. So genetic drift, I had already mentioned it in the last section. Genetic drift is going to be cause loss of genetic diversity, and it's just by chance. So it's the most common in small populations. Not necessarily the most common, it's going to work the best on small populations, because if you end up removing individuals from that small populations, you're going to have less variation to be able to choose from, and so you might see a trait that wasn't there appear. So a population bottleneck can lead to genetic drift, and it occurs when an event drastically reduces the population size. The bottleneck effect is genetic drift that occurs after a bottleneck. So you end up, how the bottleneck narrows things down, that's going to be what you end up seeing here. It's going to narrow down your population. So another one of genetic drift is the founder's effect, or the founding of a small population can lead to genetic drift. So that's going to be where a group from the main population breaks off and they go basically settle a new area. So that is another type of genetic drift. So the founder effect is the genetic drift that occurs with the start of a new population. Genetic drift has negative effects on a population, less likely to have some individuals that can adapt. Harmful alleles can become more common due to chance. So it's not always a good thing, but it's going to allow for the organisms to change. So sexual selection occurs when certain traits increase the mating success. So sexual selection occurs due to higher cost of reproduction for females. Males produce many sperm continuously. Females are more limited in potential offspring each cycle. There are two types of sexual selection. Intrasexual selection, which is going to be competition among males, and intersexual selection, where males display certain traits to the females. So that is the end of the notes for sections 2 and 3.